All right, chapter 3 is all about exponential functions and their inverses. In this first section, it's dealing with exponential functions. The basic form of an exponential function is y equals ab to the x. In this function, a is your initial value. And b is a value that is called the base, and b is usually greater than 0. Now, b can be two different things. If b is greater than 1, then it is a growth function. And if the value of b is between 0 and 1, then it is a decay function. And with either one of these two, there is a percent of increase if it's a growth function, or a percent of decrease if it is a decay function. And the percent of increase or decrease is always how far from 1 the value of b is. Now, in looking at this function graphically, a growth function would run along the x-axis and curve and go upward like so. That coordinate where it crosses the y-axis or the y-intercept would be 0, comma, whatever your initial value is. A decay function would be the flip over the y-axis of the growth function. So it would come down and run like so. And again, this coordinate would be 0, comma, a. Now in either case, the domain is going to be all real numbers. So from a negative infinity to infinity. And the range for each of these two would be everything greater than 0. And because it is greater than 0, then we have an asymptote. And that asymptote is located at the x-axis, or y equals 0. Now, understand that in a growth or decay function, if a value is put up here like a plus 3, that is going to take and shift the graph to the left 3 places. So 0a no longer becomes the y-intercept. Or if that plus 3 was not here, it was down here. Now that is going to shift our graph up. And again, 0a is no longer the y-intercept. It's going to be 0a plus 3. And then our asymptote would change to y equals 0. it would have a different y-intercept. We still would consider this to be like an initial value of just the exponential function part of it. So then, looking at a couple of examples, we have 3 times 1.65 to the x. So in this case, our initial value is 3. It is a growth function because 1.65 is greater than 1. Now, since it is a growth function, it is going to have a percent of increase. And as you recall from the previous slide, the percent of increase is how far from 1 are we. So that's 1.65 minus 1, which gets you 0.65. And so our percent of increase is 65%. Domain would be all reals, range would be all reals greater than 0. It would have an asymptote at y equals 0. Our second function here, initial value is equal to 2. This would be a decay factor, and in this case the decay factor is 0.72. And so now to figure out our percent of decrease, we would take 1 minus 0.72, which is going to equal 28% decrease. Still, the initial value is 2, decay factor 0.72, and percent of decrease is 28, because that's how far 1 or 0.72 is from 1. And the sketch of this graph, if you were to look at it, would be something like this, where it would cross the x-axis never, and the y-axis at 2. In this function up here, that's an increasing function, it would look like so. And that coordinate would be 0, 3. Now, the larger the growth factor is, the steeper this curve becomes. The closer it gets to 1, the more flat it gets. If it were exactly 1, it would be a perfectly horizontal line. Same with this. The closer it gets to 1, the more curved it's going to be. The closer it gets to 0, the more it's going to be flattened out. Now then, if we have this example here of 500 people in town, and the population is decreasing at a rate of 6% per year, how many will be in town after 8 years? So we would have to write up an equation, and it would be just in this general form, the initial value times 1 plus or minus the percent, plus if it's increasing, minus if it's decreasing, and then to whatever the number of years is, since we're dealing with years here. If this would have said something like 500 people in town decreasing at 6% per month, how many in town after 8 months? Still be the same problem. So we would start with 500, and then 1 plus 0.06 to the 8th power, if it were an increasing function. But we have a decreasing function, so therefore we wouldn't want to write this. We would want to write 1 minus 0.06 to the 8th power. 1 minus 0.06 is 0.94 to the 8th. And then you would put this into your calculator and figure out the answer to it, which it is approximately 304.78. So therefore, we would have approximately 305 people in the town. This is just some simple increase or decrease percent. 1 plus the percent, or 1 minus the percent. You will get into things a little more complex dealing with compounding. So if you have $800 invested at 8% and it's compounded monthly for 10 years, if you recall the formula for compounding, your A value doesn't change. It is still 1 plus the percent, but now you have to take the percent, which is an annual rate, and since we're compounding it monthly, we have to divide by the number of months, number of compounds in a year. And then our exponent becomes, since it's for 10 years, and we'd have to take then the compounds times the time, where these two things are the number of compounds. In a year or whatever it's talking about. So for this particular example, we would have 800 times 1 plus 0.08, and since it's monthly, we would divide by 12, and our exponent would become 12 times 10. Now when you're putting this into your calculator, don't forget, if you're going to do this, if you have a calculator that just puts everything in the same line, make sure you put that in parentheses so that it takes the whole thing as your exponent. So when you do this, it would be 800 times 1 plus 0.08 divided by 12 to the, and then 12 times 10. And that will get you $1,775.71. And so that is compounding monthly. 1 plus the percent divided by the number of compounds, to the compounds times the time. Then you will also have continuously compounded, which means it's compounding all the time. So same $800 invested at 8%, compounded continuously for 10 years. And now recall, with the continuous compounding, you use the formula P, or you can call this A still if you want. And then e to the RT. E, recall, that is a value. It represents a number like pi does. And e is the equivalent to approximately 2.7828288459. And it continues on forever. That's why they have given it a letter, because it is a pretty significant thing you need to know. You do not have to type this number in when you're putting it in E. You have that button on your calculator. Look for the LN button. And so for this particular problem, you would have 800 E, and then the exponent is 0.08 times 10. And that would get you $1,780.43. So you'd earn just a few more dollars on an $800 investment over a 10-year time. And so that ends what is all involved in Chapter 3, Section 1.